let me continue on this further for an example. So if this is my set X, believing in the union axiom assures me that the union of this set exists. And the union of this set is all the elements that are elements of X. This is an element of X. This is an element of X. This is an element of X. So these are the elements of X. So the union of X is the set of these guys. We denote this set by U of X, or union of that whole bit there. So you can think of union as removing two levels of brackets from this notation. So now I can more precisely define what a set is going to be. And from now I can also define what will I mean by a construction of the natural numbers. That's the title of my talk, so I feel it's good to define these things, as we have defined everything so far. A set is a class that can be proven to exist given the axioms of set theory. A construction of the natural numbers will be a set that satisfies all of the axioms of piano. So we need to prove that there's a set out there. It has to come from the axioms. And then we have to show that the elements of this set satisfy the properties of piano that we discussed earlier. So we will begin with theorem 2. There exists a unique set that has no elements in it. Proof. By the first axiom, there does exist a set, so call it X. By the fourth axiom of comprehension, we can pull out a subset of X by a rule. So we will consider the set Y, which is all of the A's in X that are not equal to themselves. This is our rule of inference. So now I need to show what I have said about this set, that it has no elements in it. So let C be an element of Y. This implies that C is not equal to itself. But by axiom of logic, everything is equal to itself. If something was not equal to itself, then pigs will start flying and mathematics will not have a good day. So this must mean that C cannot be in Y. So we say Y has no elements in it. By the second axiom, extensionality, if there's another set with no elements, they're going to be unique. They're going to be equal to each other by the second axiom. So Y is unique. If there's anything else like it, it is Y. QED. Now definition. This set that I have now constructed from this theorem, I'm going to call it the empty set. And we will denote it with this symbol that you should be familiar with. Now I have another theorem. I'm going to construct a set, and I'm going to call this the successor of a set. Now, by axiom 1, there exists a set X. By pairing, there's going to exist a set that, so I need two sets. So I consider X and X again. There's going to be a set that contains these two sets, which is the set of X in itself. But we don't think of a set having copies of its elements. So we think of this as just the set containing X by itself. By pairing again, we now consider the set X and the set containing X. By pairing, there exists a set containing these two. We will call it Y. It contains the element X, and it contains the set containing the element X. By axiom 5, union, there exists a set Z, which is the union of Y. By the second axiom, extensionality, any other set that has these elements as well is going to be equal to it. So this union of Y is a unique set. QED. So now, this set that I'm constructing here, by this theorem, given any set X, we construct the successor of the set X. We will denote it by successor of X is equal to Z. So, who are these successors? What do the successors look like? We know the first guy. Successor of 0 is going to be 0 and set containing 0. So when we take the union, we take the elements of here, none, by theorem 2, and we take the element in here, 0 itself. So the successor of 0 is the set containing 0, and we define this to be this symbol. The successor of 1 will then be the union of 1 and the set containing 1. The element in here is 0, so he is an element. The element of this set is 1, so this is another element. So we have this set then denoted by this symbol. And as follows, the successor of 2 is the set containing 0, 1, and 2. I need my charger. Yeah. Oh, you're right. It's time limit.
Too long the successor.
It's alive! Alright. So, as well, the successor of 3 is the set containing 0, 1, 2, 3, and we will denote it with this symbol. Dot, 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 dot. So, for a successor of a previously defined one, n, it will be the union of n and the set containing n. It will have all of the elements of n and n, and we will denote it by n plus 1. These are the successors of 0. These symbols are looking pretty familiar to us, though, as you might recognize. We will call the collection of all of these successors of 0 omega. Now this is a collection of elements defined by a rule. It is a successor of some successor of 0. So we currently have a class amongst us. The sets that we have been defining so far, I will now give them a name. I will call the sets 0, 1, 2, 3, and etc. These will be called ordinals. These are the elements of omega. Notice that 0 is an element of 1, 0 and 1 is an element of 2, and etc. And 1 is not in 0, 2 is not in 1, 3 is not in 2, and etc. We have this property of the ordinals. So now, we have theorem 4. There is no set x such that the successor of x is 0. Proof. Assume that there does exist a set x, who the successor of this set would be 0. So let's calculate what this would be. The successor of x is the union of x and the singleton of x. So all of the elements of x and x itself. So x is an element of its successor. By theorem 2, we showed that the set 0 has no elements. So x could not be an element of 0, because no one is in there. By axiom 2, extensionality, the way we compare sets to be equal or not, we know that x is in the successor of x, and x is not in 0. So these cannot be equal by extensionality. So this is a contradiction. So our set x that we assume to be the predecessor of 0 does not exist. Excuse me. Now, theorem 5, for all ordinals that are not equal, their successors are not equal. So let's start calculating this. Let A and B be ordinals, where A is not equal to B. This implies, by extensionality, that there's an element in one that is not in the other. Because if they were equal, they'd have all the same elements. So there's someone that isn't in one of them. So without loss of generality, assume that it's in set A. If it's in set B, change the names. We call set B set A. So let x be in A. So x is not an element of B. The successor of A is the union of A and the singleton A. So every element of A is in the successor of A. X is in A, so x is in the successor of A as well. So now we're tracking x, we're following him along here. X is in the successor of A. However, we know x is not an element of B. So if x is in the successor of B, we know it's either an element of B or B itself. So since we know that it's not an element of B, this implies that x has to equal B. But then x is equal to b, which is an element of A, because x is in A. But from our observation about ordinals earlier, if B is an element of A, then A is not an element of B. Since A is not equal to B, and A is not an element of B, the elements of the successor of B, then A can't be in the successor of B. The successor of B only contains those two types of elements. But A is in the successor of A. So, we have shown that there's an element in the successor of A that is not in the successor of B. So, by application of the extensionality axiom, we know that these sets cannot be equal. Q and B. So, oh no, that disappeared. That's not good. Okay, this says Peano's axiom 1. We have shown Peano's axiom 1 such that there is an element called 0. That was our theorem 2. The second axiom of Peano was that for every element there is a successor. So theorem 3 proved that for every set there exists a successor. Theorem 4 proves the third axiom of Peano, which said that there is no successor, that 0 has no successor. So that is what we proved with theorem 4.
But no number has 0 as a successor.
Yes. Okay. Yes. No number has its successor as 0. So that, Peano's axiom 3, we have proved now for theorem 4. And that no two numbers have the same successor was proved in theorem 5. That Theorem 5. Oh. But wait. This is a class of ordinals. How can we know if this exists or not? We would need to be able to... The class of ordinals is all of the successors of 0. So we see that we can create all of them. We can create every successor. These successors do exist by the 5 axioms we are assuming. So we recursively repeat the successor construction on 0 to generate these elements. But now the real question is there a set containing all of these guys? Does something exist that contains all of these sets as elements?